Hello everyone. In the lesson today we are going to learn about confidence intervals for a population proportion. So the learning objectives are two. First, determine from a large sample an approximate confidence interval for a population proportion. And we are going to see why is it an approximate one. The second learning objective is outside the syllabus, but as always it is good to know where from the results come. So in the first learning objective, we are going to use the distribution of the population proportion. But then here we are going to prove why the distribution is the one that we claim and use in part 1. In real life, at the TV, in the news, we are often presented with estimates of a population proportion such that in an election, someone might say, if the election is held tomorrow, someone might say 67% of the population would vote for party X. Or 40% of the world population had COVID. Or 80% of the companies do not employ smokers. So these are examples of population proportion. Of course, not the entire population was surveyed in order to find these results. To estimate a population proportion, we consider taking a random sample. And we need to see the distribution of the random sample variable, the sample proportion. This will give us the estimate. Let us start by looking at an example. I want you to pause the movie and read it yourself. From the data, the population of the sample, let us put it PS from the sample, is 362 over 653. So it's 55.4%. And the sample size is 653. And Q, probability of a fail, is 291 over 653. Please notice that these two add up to 1, and this one is QS, specific for the sample. Now PS, all proportions from all samples will form a distribution. And this distribution is in your formula booklet. It's called the approximate distribution of sample proportion. The distribution of PS is normal with PQ over N, where P is a probability of success and Q is a probability of fail. In our case, P is PS and Q is QS. So what we are saying here is that PS lies on this distribution, which is normal with this mean and this variance. Therefore, a confidence interval for this will be P minus Z 0.975 times square root of PQ over N, P plus Z 0.975 times square root of PQ over N. And this will be our confidence interval, 95%. In my case, it's going to be 362 over 653 minus 1.96 square root of 362 times 291 over 653, comma, 362 over 653 plus 1.96 square root of 362 times 291 over 653. So this one is about 0.516, 0.592. For the sake of comparison, let us remember that when we have X normally distributed with mu sigma squared, then the sampling distribution of the mean has this distribution. So the confidence interval was X bar, the statistic, which in my case is P, that's what I test in reality, minus Z times the standard deviation, minus Z times the standard deviation. And here the standard deviation is square root of the variance. So it is exactly the same formula. Now on the next page, let us see where from it comes. This part is outside the syllabus, but we already know that we understand better if we know where from the results come, so the proofs, and we also are able to build ourselves new knowledge so we can solve problems outside the box if we understand things rather than only applying them. So I'm sure you can all follow me. To estimate the proportion of voters who intend to vote for party X, we take a random sample of n voters, and this is a sample size. And we ask them who intends to vote for party X. Let us assume we take 5,000 voters. So n equals 5,000, the sample size, and let's assume that 3,000 vote for party X. So the sample proportion P will be 3,000 over 5,000. So it's 60%. This is P, is the sample proportion. However, this is just one particular sample. This is what we do in reality. We just take one good sample, unbiased. But we want to know for all samples of size n, what is the mean and the standard distribution of the proportion. So let's form this distribution. P is x over n, where n is a sample size and x is the number of successes. So as you see, I take each voter and I ask him, do you vote or you don't vote for party X? So I'd allocate a 1 and a 0, depends on what he votes for. It follows then that X has a binomial distribution with n and P, where P is a population proportion. I need to get back and change a bit my notation, because I have two P's denoted the same thing. So let me put PS for the sample proportion, PS for the sample proportion, PS, and P is the population proportion. So P is for the population, and PS, I don't know the proportion in the population, and PS is for the sample. Let us now start looking at the distribution of PS. What we do is that we take n voters one by one and we ask him, do you vote or you don't vote for party X? Therefore, what we do with PS is that PS will be formed by Y1 being the first person who I'm taking and asking, Y2 plus Y3 plus Yn over n, where each of the Yi are binomially distributed with 1 and P, because I ask each person once, so one trial, and P's probability of success, meaning probability that the person votes with the party X. So I know that the expected value of Yi is 1 times P, so it's P, and I know that the variance of Yi is 1 times P times Q. So it's P brackets 1 minus P. Now I'm ready to find the expected value of PS and the variance of PS. You might want to stop the movie and try yourself. Now, as you see, expected value of PS is expected value of Y1 plus expected value of Yn over n. Each of this is P, so I have NP over n, which is P. Variance is 1 over n goes outside as 1 over n squared times variance of Y1 plus variance of Y2 plus and so on. Each variance is PQ, there are n of them, divided by a square, so I get P brackets 1 minus P over n. Let's start and pause a bit. What am I actually doing with PS is that PS is the sampling distribution of the mean of Y. So I'm taking y1 plus y2 plus n, so that's a sampling distribution of y for samples of size n. Therefore, I can apply central limit theorem to say that PS is normally distributed with mean is P and variance is P brackets 1 minus P over N. We know that in order for central limit theorem to be applied here, the sample size needs to be big enough, and we take n bigger than 30 as a good practice. We also call this an approximate distribution. Therefore, the confidence interval we're going to find will be approximate for a couple of reasons. One, because we use central limit theorem, the parent distribution is not normal. The parent distribution is binomial. So that's one reason. Second, we do not apply continuity correction, as we saw before. So therefore, the confidence interval will be an approximate one, but it's accurate enough to be reliable. In all this process, we need to ensure that the usual conditions for using the binomial distribution are met. So there need to be a fixed number of trials, only two possible outcomes, success or fail, and trials must be independent from each other, the probability of success staying the same. These last 7 minutes proved why the distribution of the population proportion is normal and has the parameters that are here. Now I can use this distribution to find confidence intervals for the population proportion, and we've done this on the previous page. Well done for coping with this difficult concept. See you soon.